So we've gone through pH calculations with the ice chart of acids and bases, weak acids and weak bases. And I figure for as important as this is, it's a good time to do a practice problem each way. One starting with a weak acid and one starting with a weak base. I'm thinking this is going to be one movie, but we'll see if it gets long. It might be two. So check to make sure we got the acid and the base in this one. The practice problems that go with this are attached to the material. There's only two. The first one's pH of vinegar, acetic acid, COOH, CH3COOH, given your Ka, and I want to know the pH. First thing you do is write your equation, and if you want to label your state symbols, you can. If you're writing it for you, you don't need to. Take the acid I gave you, CH3COOH. It's going to be aqueous, and I'm always going to throw it in liquid water. That's what these are. Throw it in liquid water. Because it's an acid, it's going to donate a proton. And water is going to take that. H3O plus. And remember, we can write H3O plus as H plus because we don't really care about the water. So that was step one. Step two, you can either write your Ka expression. I'll do that at the bottom. You could write that now, or you could set up your ice chart. So I want to know, as this goes to equilibrium, as this acetic acid breaks down, what's going to happen? So I'm going to have my initial, my change, and my equilibrium value. Let's see what I'm going to include. Not that. So I need CH3COOH, and that's going to be the one side of the equation. I need its conjugate base, the acetate ion, and of course, our dear friend that makes it, the acid on that side, the H plus, and we need concentrations across the board. So initially, I start off with 0.50 molar acetic acid, with it not broken down at all before I throw it in the water. So initial is before it ever hits the water. I know that equilibria for acids and bases are quick, so once I throw it in the water, the acetic acid is going to break down, and it's going to make me the acetate ion and H plus. Okay, cool. So at equilibrium, I've got 0.50 minus X for my concentration of the acid. It's broken down, and it's made X molar CH3COO minus and H plus. I know from the stoichiometry of the reaction, the 1-to-1, that I'm making X and X of those. All right, I'm going to take this mess at the top off and put your Ka stuff up there. I've got your value at 1.8 times 10 to the negative fifth. You were given that. So I'm going to use that up here to rewrite my equation just to make sure you guys can see. So my Ka is going to be 1.8 times 10 to the negative fifth. But more importantly, it's going to be my concentration of CH3COO minus. It doesn't matter if you write that or the H plus first. And H plus on top, and CH3COOH on the bottom. Same as our K expressions always are. Now, with our K expressions looking like that, it's going to be a little bit messy. It's going to come out as a quadratic equation if I can't ignore X. Like I said before, on your test I would expect to ignore X. In homework though, and in practices, maybe not. So let's check. One of the ways I know to ignore X is if I divide my concentration, 0.5, by my Ka, 1.8 times 10 to the negative fifth. If I divide that and get bigger than 500, ooh, like 28,000. If I divide that out and get more than 500, yeah, I'm pretty good for ignoring X. So guess what I'm doing? Yeah, he's gone. So my equation then is going to be instead 1.8 times 10 to the negative fifth. That's X. That's X. And this is 0.50. Check out that laziness. I just turned that into my equation. So what I end up getting is that X squared equals 0.5 times 1.8 times 10 to the negative fifth. I end up being able to multiply that out pretty easily. I end up with x squared equals x squared equals 9 times 10 to the negative sixth. So when I solve for that, I get that my x is 0.003 molar. And that's my concentration of hydrogen. So to get my pH then, I take negative log of that, and my pH for this solution of acetic acid is 2.52. I double check, I think it through, that is a legit pH between 0 and 14, and it is legit for an acid being less than 7. So that's a pretty good setup there. Like I said before, we spend a lot of time on these things dealing with acids rather than bases. I remember feeling very comfortable with acids and not so much with bases because we've practiced them less, even though the pattern is the same. So I've got for you Kb for bases equals 1.7 times 10 to the negative ninth. Oh, yeah, that's going to let me ignore x, because if I divide anything by that, it's going to be greater than 500. For this thing called pyrimidine. It's one of those weird organic bases with a nitrogen in it. So, and I've got concentration of C5H5N, pyrimidine, is going to be 0.100, I believe, molar. All right, so let's see what we can do here. Going to do the same thing as before. Going to do C5H5N. Going to label it aqueous because I'm going to throw it in liquid water. That's what I'm going to do. Always throw it in liquid water. It's a base. So unlike before, it's going to steal a hydrogen from water and leave me OH minus. Even Arrhenius said OH minus is a base. So there we go. I made OH minus. Good. All right. That's what's going to happen. Let's start this. Let's say, all right, what's important? C5H5N, not water. And C5H5NH plus, sure. And OH minus, very important. There we go. That's what I need. So I need my initial. I need my change. And I need my equilibrium. Then we're going to do the same thing as before. Clean up the top. And make sure you can check this out all at once. Initial 0.100 molar. I didn't throw it in water yet. So nothing happened. It has not reacted to any extent we talk about. Same as with the acid. I'm going to break down my weak base and make its ions so that at equilibrium I have X concentration of those. I do have 0.100 minus X technically, but because of the small kb, I already know that gone. If I wanted to check 0.1 divided by, oh gracious, 1.7 negative 9. It's like millions, maybe billions. That's cool. So this is what I've got so far. That's what I'm going to use in my Kb equation. Kb equals. I'm going to come back to that 7 whatever and put this in. Same as I did last time. So Kb products C5H5NH plus and OH minus over concentration of C5H5N. Cool. So, going to go the lazy route. You could leave that written on your paper, but because I'm the teacher, I can be like 1.7 times 10 to the negative ninth, and just throw that in there for my Kb. What do I have? X, 0.1. I feel like that's x squared equals 1.7 times 10 to the negative 10th. Because this happens when you multiply by 0.1. I already did this one. So I've got that x equals 1.3 times 10 to the negative 5th, which is not quite as neat this time. Last time we had the concentration of H+, we've got OH-. So we need to do a little bit of fancier working to get the pH. Nothing crazy, but let me think. If I want pH, I know that pH equals 14 minus pOH. And that's what I'm going to use to get here. So, let's set it up. pH equals 14 minus the negative log of 1.3 times 10 to the negative 5th. Awesome. For this, I got, for this part, the log, I got 4.885. So 14 minus that gave me a pH, and I hope you guys can still see this. I'll hoist the board when I'm done. 9.12 when I finish that problem. Is this in the pH range we're allowed to have between 0 and 14? Yes. Is this a basic solution? Yes. And here's what else is cool. That's not a very big KB. So I wouldn't expect it like a strong base to be nearing 14. I would expect it to be kind of a poopy middle of the range base, a weak base, a really weak base by the looks of KB. And it is. 9 is not all that exciting. So that looks correct to me. Your basic setup for these no matter what. Write your equation with water, figure out reactants and products. Set up your ice chart and solve, or you can write your K expression first. Either way, once you've got the equation, you're set to do either of those. Solve for H or for OH. If you've got H, negative log it for your pH. If you've got OH, 14 minus negative log it for your pH. That works either way. So hopefully these practice problems helped you out. And we'll move on from here. This is the big calculation from this chapter.